I'm really not. What? All right. Thank you everybody for coming to the Utah Go meetup for June 6th. I'm really, really excited about this one. I've been waiting for it for basically ever since he's announced it. So we'll do a couple of quick housekeeping things and then go right into it. I always warn people, these square things above your heads are microphones and they are really good. They will zoom in on you when you're talking and pull you up in the audio and in the recording. So you might be whispering, but they'll still find you. They'll have a section here at the end once they'll turn off the recording, and then you can whisper all you want. Down here at the bottom are links. One of the main things on there is Forge Slack. So if you want to go somewhere and throw shade or have otherwise intense discussions or sometimes not intense discussions, you can go to the Forge Slack, including dedicated channels there for jobs and hiring. So I always point those out specifically because they're good resources to use. If you want to speak at this meetup, which is, you might also have come here for the Women Who Go meetup, we're co-located. So if you're looking at either of those, the kind of post to both of those meetups, but it's one meetup. But if you want to speak at this, you can go to Paper Call for Utah Go Lang and submit. I've always said, and I will keep saying, any submission accepted. Which sounds like I'm desperate, but it's not. I want anybody that wants to speak to be able to speak. Even if you don't think it's a full hour's worth of content or half hour, if it's just a small bit of content, but something you want to talk about, please submit here and we can work you in, even if it's leading into somebody or maybe with a bunch of other people that want to do smaller talks. So don't feel like it has to be some big grandiose thing, something really, really cool, like building an entire video game in Go for the Game Boy Advance. Smaller things are absolutely great, and we'd love to have anybody and everybody come and speak here. And that's it. So I've done all of my rants, and like you might have guessed what I was talking about, our topic today is about building Game Boy Advance games in Go, which is really, really exciting. This is by Brandon Atkinson, who is a member of the DevX team here. So take it away, Brandon.
Yeah.
Oh, wait, I almost forgot before, and this is the last chance. So if you really want one of these, if you want to scratch over.
I have more, I just forgot to bring it up.
Okay, never mind. We'll pretend I only have one more. So, Brandon, it's your choice, blue or gray? Blue. Okay. Got a gray stuffed over speakers along with a bunch of stickers.
There
So
you go.
thank you for that.
This
And-
is the reason to come to the.
yeah, if nothing else, don't put the stickers and the gophers. Great. Awesome. Thanks, man.
Yeah. All right. Go ahead and go ahead and have a talk about one of the more absurd things that you can do with Go. Okay, so like Carson said, I'm Brandon Atkinson. I'm a platform engineer here at Weave, working on the dev experience team. And our primary language that we use here is Golang. And I have somewhat of a academic background and enjoy some of the more esoteric sides of engineering. And so we're going to talk about something today that is a little bit more on the esoteric side. But to start out, we're going to dive into the Game Boy Advance. So my guess is that at least some of you remember owning one of these systems. It's one of my, fond memories of growing up, getting a Game Boy Advance. It came out in 2001. It's this little teeny handheld, 240 by 160 LCD, not backlit. If you remember, the colors were really difficult to see. It's the successor to the Game Boy Color, which I'm sure a lot of you also remember that system. Sold 81 million units, so decently successful. But the most interesting fact about the Game Boy Advance that I think comes up when you research it is it's actually Nintendo's very first 32-bit console. Not very many people realize it feels like a 16-bit console, but it actually has 32-bit registers and a 32-bit CPU. Can run 16-bit instructions, but can run 32-bit instruction set on a Game Boy Advance. So that opens up some opportunities. There's this thing called TinyGo. And I don't know how many of you have heard of TinyGo before. It is a compiler for small places, is how they refer to it. And so the way that it works, last session we talked a lot about compilers. Last session we talked a lot about compilers and how compilers work. And in a compiler, you have like a front end that does the lexing and the parsing, and then you get into LLVM, and that's the back end. Well, there are some compilers with a separate back end, right? And the back end is what takes this parsed and lexed code and turns it into machine code. LLVM is a back end that you can stick onto a compiler, and it can target a ton of different platforms. And a lot of different compilers use LLVM in order to target a bunch of different stuff. So TinyGo took this idea of like, hey, we'll take all of the Go front end stuff from their compiler, the type checking, the parsing, all of that, and then we'll like move to an intermediate representation, which is like something in between LLVM and Go, and then we can translate the intermediate representation into LLVM code, and then LLVM can target tons of different stuff. It can target all sorts of different systems, all sorts of different instruction sets. And so it's a really powerful compiler that has a lot of options that you wouldn't get with the regular Go. So one of the targets that's supported by TinyGo because of the LLVM support is the Game Boy Advance. It can compile to this 32-bit instruction set. And so that opens up this opportunity for us to write raw Go code, compile it with TinyGo, and then run it on the Game Boy Advance CPU. So this is about the point at which I started 6-7 months ago. I was like, okay, like conceptually, I have TinyGo, I have Golang, I have the ability to compile to the Game Boy Advance. What would that actually look like? And so you start digging into the constraints on this early 2000s handheld. You get a 16 megahertz CPU. That's megahertz, not gigahertz, right? You get 32 kilobytes. The way that RAM works is really interesting. You have 32 kilobytes of RAM that's close to the processor. It's not a cache, but it's close to the processor. You have 256 kilobytes of external RAM. Like that's your beefy, that's your big RAM right there is this external RAM. And then you have 96K of VRAM. That's all you get for an entire game is basically a sum total of slightly over 256 kilobytes, right? You have 16-bit color. So a lot of us are used to working with 32-bit color where each channel is 8 bits. The Game Boy Advance does RGB. It actually does it kind of weird. It has blue channel, red channel, and green channel. Each channel gets 5 bits for 16-bit color. You get 6 video modes. If you've heard about mode 7 for the SNES, this is a very similar. They stole a lot of these ideas into the Game Boy Advance. So you have like these video modes that you can use. There's no operating system, there's no system calls. You can't make a call to the GPU, right? None of this. It's just kind of as close to the metal as you can get, really. So with this in mind, we have a tool chain. We have an understanding of the fundamentals that we're going to have to be working against. So let's get started. How do you get started making a Game Boy Advance game? Here you go. So the first thing you got to do, right? Install TinyGo. And there are good instructions there. I've left a bunch of links in this talk. I intend to post it to the Forge Slack because a lot of these resources I'm not going to have time to fully cover today in depth. If you want to follow this talk more closely and actually click through the links and look at stuff, it'll be available on Forge Slack. So first thing, click this link, go install TinyGo on your system. The next thing, you're going to go out to the internet like I did, and you're gonna search, how do I build games in Go? How do I build games for the Game Boy Advance in Go? And you're not gonna find hardly anything. This is kind of an undiscovered, uncovered topic. There are very, very few resources. And I will warn you, almost every resource that I have found that will teach you how to make games for the Game Boy Advance in Go are terrible. Don't follow them because they do a lot of things wrong. They basically get the minimal working version, but they use the wrong video modes and they don't have good tools in place to convert graphics. it's a bad time. So I've listed a couple of things that have some useful ideas that you can pull from. But what you're really going to want to do, if you're looking to do this the right way, you're going to go look at C references. And there are so many. So the homebrew scene is what, I don't know if people have heard about that before, but homebrew is this idea that you take this device that's closed source, that's not available, and you make your own code for it and place it on that device, right? What we're doing now, this is homebrew. And that scene was actually pretty big in the early 2000s with the Game Boy Advance. But it was all written in C and I think maybe some C++. But those people, right? Those people provided a lot of great resources to the community around them. You feel like you're going through the Wayback Machine because all of these websites are super old school, but they're great. They have tons of really useful detail. The resource that I use the most and would highly recommend, we're actually going to go ahead and look at it. Yeah, welcome to the early 2000s web, right? But this is great. This has stuff about the Game Boy Advance hardware, stuff about the keypad, bitmap modes, sprites. It will give you a mathematical background, has BIOS calls, right? Would highly recommend you read through like memory layout, right? This is a great resource. There's another one I think that's listed later on. Oh, this one right here, GBA Tech. So this is like, these are technical details of the memory layout of the Game Boy Advance. Like you have to read through this stuff to figure out what you're doing. And it has display registers and sound registers and talks about the memory layout and like the memory addresses for all the various things, right? So these are the kind of resources that you're actually going to have to figure out how to look at and how to read through. You're not going to find a Medium post that's going to give you the stuff that you need, but there are good resources out there if you're willing to dig in. But here's the thing, I don't want you guys to have to do that because that takes a long time and it's really hard. So if you're not super interested in the idea of digging into all of that nuance and technical details, I've actually provided an open source game that you guys can just kind of steal from. And I would highly recommend, if you're going to start, if you're like, hey, this was a cool talk, I want to try and do this, just steal from me.
You need an emulator to run your game?
You do need an emulator to run your game.
Yeah, I downloaded one last week.
So I won't talk about emulators any more than that. Just say.
Download your game. I want to play it. And
Yeah.
I'm just making sure I'm all set up and good to go.
Yeah, it doesn't come packaged with an emulator. We'll actually talk about, there's some things that you can do to mitigate needing an emulator. If we get time, we can talk about that in a little bit. But yeah, so emulator, if you go look at this, and we'll actually spend quite a bit of time looking at this repo, because I'm going to talk about the different things. Like this is the repository. We're going to talk about the various things that exist here, how the code's laid out, how you maybe would want to think about digging through it, right? But this is going to be an excellent resource for you if you're interested in this, trying to figure out how all of this stuff works. So I mentioned earlier, the Game Boy Advance does not have an OS layer. There's nothing in between you and the hardware. You're basically expected to have full control over the device. And so one of the things that you're going to have to do to make a game here is talk to the hardware, which is not something that we're really used to doing in Go, right? Because we expect to say, oh, I need to make a file. Let me call the OS package, or like I need to run a command in the shell. Like let me call a package that will do that for me, right? None of that exists at all. There's not even a way to print text on the Game Boy Advance. Like you have to do everything from scratch. So talking to the hardware is like a fundamental piece of how you need to interact with the Game Boy Advance. So hardware registers. Is there anybody who has like a decent grasp on what a hardware register is that would maybe like what's a hardware register?
I mean, it's just like a bunch. It depends. They're essentially just like a section of volume that's very fast. It's typically like you have like 32 bits, then it's like a 32-bit register. It holds a piece of data. Yeah.
Yeah, I mean, yeah, exactly, right? It's a spot in memory. It's usually given a memory address, right? But the key piece I think to realize is this piece of memory is special because you can write to it from code, but the hardware can read from it, right? So it's like this thing is not just arbitrary, like you can use this section of data for whatever you want. No, the hardware has specific expectations about what this memory means and what it's going to do. And so when you write to it, things will happen on your device because there's a hardware piece that's reading from it, right? Or interacting with it, writing to it, right? It's shared memory between your program and the physical hardware that runs the device. So the first concept is memory map. This is the first package that we're going to go into. And the fun thing is, I didn't actually know if I was going to be able to do this. My goal was to make a game that was as purely Go as possible. You can see I hit 99.6%. I was really close. The only C code, there's 11 lines of C code that I could not remove, and they are in the memory map package. So we're going to go into internal. We're going to go into the hardware section. We're going to go into memory map. And then we're going to look first. Well, let's look at memory map.go first, and then we'll look at the header file. So I don't know if you guys have worked with Seago before. Seago is a way that you can compile Go code along with your C code so that they can interop and work with one another. And it's basically the only consistent way that I could figure out to get some of this hardware interacting behavior. So this package, you see I have a couple of constants defined up here for sizing and offsets for memory. You'll see I have some.
A bit bigger.
You can do that. How's that?
That's perfect for me.
Right.
It's great.
So you'll see I have memory addresses for offsets. You'll see I'm doing this really funky thing, unsafe pointers that we'll talk about in a little bit, defining slices. But I have these two functions, getReg and setReg. It's using generics, which I think is super fancy. And again, I'll talk about that as well in a little bit. But the core idea here is that I'm going to take, for getReg, I'm going to take a memory address, and then I'm going to call out to C. I'm going to get that value, and then I'm going to return that memory address, like whatever was there, right? And the same thing for setReg. I'm going to say, here's a memory address. Here's a value that I want you to place in that memory address. I'm going to call out to C. I'm going to set that memory. And you might say, well, I can do that in Go, right? Like, there's no reason that I couldn't set the value of a pointer. Why do we need to call out to C? The reason that you need to call out to C is because Go is selfish. Go does not like to share. There's this thing called the Go memory model. And Go is very, very convinced that it owns all of the memory. It gets all of it. So if the OS says, here's a block of memory for you, it says, great, that's my memory. It's not designed to share memory at all. And that becomes a problem when you're sharing memory with the hardware, right? The hardware needs to have this interface where it can talk to your code. And Go says, no, I'm not going to talk to the hardware at all. I own everything. So you add this volatile keyword right here. This is the key thing that's going to make it possible for us to talk to the hardware. The C code, like the C language, has this concept of volatile memory. It's concept of memory that I don't own. Somebody else might also be reading and writing this memory. And so again, like these are pretty simple functions, right? I have a macro definition that's going to get expanded. And basically, I'm just going to either return the value at that memory address. I'm going to set the value at that memory address. And because it's volatile, because I hand the execution off into the C runtime, and the C runtime knows that it's volatile, this is what allows you to talk to hardware registers safely. So anytime you need to read or write from hardware registers, you have to use these functions. All right. So, okay, we already kind of talked about this. Get and set reg. The way that these work is when you have the registers defined that you need to set and talk to, these are the functions that will let you do it. And then the type system. Now we need to talk about the type system, because another thing that you may have noticed here inside of the memory map package is that I am not using regular functions, I'm using generics here, right? I have a sum type, I don't know if that's the technically correct term, but I have a type that's made of multiple types, right? Called reg. And this type contains all the different register types that I define in the language. And the reason that I do it this way is because, well, let's go look at some of the registers that we're going to have to write to, right? So we're in hardware. Display, for example. There are a bunch of different hardware registers that control how the Game Boy Advance's display mode works, right? So you can change, remember I talked about mode 7 with the Super Nintendo, right? If you want to change to mode 3, which is the mode that we're going to use for this Game Boy Advance game, you have to write to a hardware register. The hardware register is defined right here, control. You can see I've included tons of documentation, right? Control is the LCD control register used to set up and configure the display and other video data. Each of these refers to the different bits that you can set to change things like the display mode, the active page, the sprite tile map mode, which backgrounds are enabled, right? And you can see that this specific register is of type display control. The other thing is, you'll see down here, there are a bunch of different modes, right? So you have mode 0, mode 1, mode 2. We talked about different video modes. These are all of that same type, display control. And the reason I do this is because now there's tight coupling. There's a tight coupling at the compiler level that tells me, hey, this display control register is just a random uint16, right? Like it's a pointer to a uint16 register. Most of the registers on the Game Boy Advance are 16 bits. Even though it's a 32-bit system, it's kind of confusing, but they're 16-bit registers. And this is a really nice way to organize your code such that you don't accidentally use the wrong values with the wrong control registers. And actually, I don't see this used in any of the, I talked about the C documentation, right? Leverage C. I didn't see this pattern really used anywhere, but it's a really powerful pattern that will help save you from potential pain. In C, they really love relying on like naming conventions, right? Like you're going to prefix it with the name of the register that this goes with. But I feel like the type system's a lot better suited for that. So you can see that these registers are defined with their associated values that need to be set to. And then you can imagine how this then could be used in the memory map inside get and set reg to make sure that you're setting the register to a valid value. Right. The other thing that we're going to talk about, and I kind of spoiled this already, but think for a minute, because I showed you this GBA tech manual earlier, right? So we talked about display control where you set the mode for the video. You can see here in this documentation, LCD control, the read-write register is 2 bytes, and its hex address is 4 million. So at hex address 4 million, there lives a 16-bit unsigned integer that you need to write to change the video mode. In Go, how would you tell the code that you needed to create a pointer to a uint16 that lives at a specific address? Right? Like that's a weird thing. We don't do that. We don't walk in and tell Go like, hey, this is where my memory should live. That's why we have a garbage collector, right? So the way that you do this, this is the most cursed Go code that you will probably ever see. But the way that you do this is you take a uint pointer, right? So uint pointers are Go's type, where it's like this is an unsigned integer, but it's an address value. And you cast that uint pointer to an unsafe pointer to let Go know, hey, hands off, I'm doing crazy crap right here. I don't want you to tell me how nuts I am. Just let me do it. And then once you cast that address to an unsafe pointer, like it was a number that pointed to a specific address in memory, we're going to convert it to an unsafe pointer. Now we're going to convert it back into a pointer to a value. So palette value is an alias to a uint16. You can see right up here. Palette value is an alias to a uint16. So basically we're going to say this address is an unsafe pointer, but actually it's a pointer to a uint16. And we're going to assign that to here palette start. So this is where all the palette memory starts. And you do this all over the place. I do this in display. You can see this pattern. IO adder, actually, it will be easier to demonstrate that. The IO address, this is where IO memory starts. We're gonna add hex 4. We're gonna cast that to an unsafe pointer, and we're gonna turn that into a pointer to a display stat, right? So this is a way where you can like force memory to be laid out in a very specific way. The downside of this is this will break the regular Go compiler. It will not be happy. Like you can't actually run this code outside of a Game Boy Advance now because it will be like, you're trying to access memory that I am not making available to you. So as soon as you start adding this stuff into your code, there's no more chance to like try and debug on your console or anything like that. Okay, so we have some foundational pieces, right? I haven't gone through all of the foundational pieces, but I think enough that you can get a picture of like, okay, so I have these hardware registers that have values that I need to set to them so that I can configure how stuff interacts. And there's stuff for displaying things, and there's stuff for audio, and there's stuff for controlling like the buttons that are pressed. How would you turn that then into a game engine, right? Because the first step we want to do is create a foundation that we can build a game on top of, right? So we've gone from the hardware level, we're going up a level, we're going to say we need to create a game engine. So the first thing is requirements that I had when I built this game engine for myself is I wanted something small and lightweight. I wanted it to be something that I could develop completely on my own. Like there are game engines that are the responsibility of entire teams. I wanted it to be simple, easy, and also fit to purpose was a really important one. I don't have a whole lot of memory, so I don't really have a whole lot of room for abstraction, right? It needs to be fairly flat. And so I set out to create something that would be useful to me as I'm developing a game, something that I could build on top of and build a couple of different types of games if I wanted to, but that would still be thin enough that I wouldn't end up with 0 CPU time left to actually do gameplay. So the broad organization of this project, I have the assets for the game live in their own folder. CMD is an important one that I hope we'll get time to talk more about, but I'm not sure that we will. There are lots of different supporting tools that you need to make a Game Boy Advance game. One of the classic examples is you only have 96K of VRAM, so you can't even fit a single PNG file. So if you want to do textures, you need to convert any sprite or image file into a specific Game Boy Advance supported format. So the commands that do that, that convert that data into the correct format, live inside this folder, right? And the nice thing about that is because it's all packed up and built into the same thing, then when I compile it, it's very easy to run generation on all the assets, stick them into a generated folder in the gameplay area, and then have them work. Gameplay is split up into scenes and game objects. So you have the conceptual idea is you have different stages in a game, like you have your menu, and then you have your main gameplay, and then maybe you have a game over section, right? And these are all considered different scenes is kind of how I conceptualize them. A lot of game engines kind of work like this. And then each of those is populated with different game objects. So you might have a player, you might have some text, you might have a score object. Those all live inside of gameplay. And then inside internal, this is where the real meat of the game engine lives. So you can see there's an alloc spot. We're going to talk about custom allocators. There's assets again. So once I take my image assets and generate them with command, then they get stuck inside the engine. There's a display section. There's a game section. This is like the main game loop. Make sure that the game runs repeatedly at 60 frames a second. There's the hardware section, which we just talked about, how you talk to the internal registers. There's a key thing that kind of maps the low-level key handling functionality to a little bit of a higher level so it's easier to use. LUT. Does anyone know what LUT stands for? Lookup table, yeah. So I generate lookup tables for things like a sine wave, right? Sine wave is very computationally expensive. I only have 16 megahertz, so I generate lookup tables for a sine wave. Math. There's actually a whole bunch of interesting stuff around the math package. When you only have 16 megahertz, you can't actually use floats. You need a different solution than a float 32. And so the math package does a lot of that lifting for me. So just some teasers. If you're interested in any of that stuff, this code's all available. Go check it out. But this is kind of the broad layout.
It's also worth noting as a complete aside, but very related and not very often talked about. This is why we have the stupid algorithm coding interview challenges, because it was relevant when you had nothing to work with. You had to be clever and all the clever things were important.
Yeah.
Can you even use a float? Like, would it crash? Because like you said, we can only use 16 bits most of the time, right?
So, okay. So it's a little bit complicated. The CPU can execute 32-bit instructions, but it has a 16-bit bus. So moving those instructions into the CPU is slow. And it doesn't have any hardware understanding of what a float is, like most modern systems do. So like, yeah, you can use a float. When I say you can't use a float, that's wrong. You absolutely can, but it's going to be really, really slow.
So is it gonna use like 2 buses?
So it'll take multiple cycles to move that. It's gonna, one cycle it'll move half the float, the next cycle. And I shouldn't say cycles because I don't know exactly how many cycles it takes to move memory across the bus.
Multiple cycles.
Yeah, but it's gonna move it in parts. And that's not really the most concerning piece. The most concerning piece is float math is actually very complicated. And when you compile like a floating point arithmetic operation down into assembly, it gets really big because what it's actually doing, my understanding a lot of the time, is it converts it to a fixed point, and then it does a bunch of arithmetic on a fixed point because that's a lot easier. But there's just a ton of bloat that gets added in order to support that. And you don't notice that. That happens actually on, I think on most CPUs. Like a float 32 is just more difficult to use than like an integer, like a 32-bit integer, right? And there's been a lot of work to abstract that away and make that feel like it's not so slow. And like some computers do have, like GPUs have tons of hardware specifically designed to work with floating point. But Game Boy Advance has none of that. So like the real issue is the speed of the CPU rather than it can't compile.
Can't bring everything down.
Yeah.
So,
Yeah. And again, so this is kind of the deal with Game Boy Advance. There's always an accept or an aside. Like you can use a couple of floats, right? Like you can use a handful of them. But one of the first games I built was a matching game. And I built a board of, I think it was like 5 by 3 or something. So like 15 or 20 cards. Each of them was assigned 2 floats for their X and Y position. And when all of the cards moved simultaneously, I went to like 30 frames a second. Like it significantly dropped the performance of the game, right? So that's kind of the deal is you can use a couple, but if you use like 50 and use them all at the same time, then it's gonna slow you down. And there are tricks to get around that so that you can totally move a bunch of, like, for example, you could totally move 15 cards along a smooth path using fixed point numbers instead of floating point. Which we can talk, I mean, if people are interested, we can talk about fixed point numbers right now, but I have some time later as well if we want to talk about it then. Okay, I'll move on for now. And just raise your hand and tell me to go back if you want me to. Okay, so allocators. Memory allocation is a very interesting problem. If you are a Go programmer, you just don't ever think about, right? Like one of the benefits of being a Go developer, if you've done Go or Python or Java or any of these languages that handle all of this allocation for you and do garbage collection for you, you don't ever really think about it. But the point of allocation is we have this interesting problem at the foundation of computing, where we have these objects that may have unknown memory sizes. And we need to figure out how to slot them into finite memory, right? And we might have enough available memory that our program could run theoretically forever and never crash because there's always enough memory for it. But you have to like add things in and take things back out. And you have to do that in such a way that if you need something, it's there. And when you don't need something anymore, it's gone, right? And usually we think about this, right? In C, we're like, oh, like this is memory management. This is how you manually memory manage, but it's actually even more fundamental than that, because the way that you do things without an allocator is you actually have to specifically say, this is where my object lives. Like, this is the memory. There's no stack or heap. It's just like, I'm taking this memory for my stuff. If you're in assembly and you have very limited memory, that's what you do. There's no allocation. You just put stuff where you want it and have to remember where everything lives. So this abstraction layer says, hey, instead of you having to tell me exactly which point in memory you want to exist, you can just say, I have some data, find me a spot in memory where I can stick that data and then give me the address. So the reason that you need to do that, so you don't need to do that for most of your stuff because Go still handles a lot of that stuff for you. But the VRAM section, that's the video RAM, you have 96K of it, and you're gonna need to load assets into that VRAM. And in a nice game engine, you would like to be able to load in those assets without having to explicitly think about which slots each of those assets live. So I have this whole section of custom allocators designed to make that process easy so that you can say, I have a bunch of different sprites. I'm gonna like go along for some period of time and have my memory split up amongst a couple of different sprites. So at the top, we initialize VRAM, and then this is an example we've run for a little while. There's some free space in here. There's some sprites that have been allocated. And then we're gonna go down. Here it says free sprite 5. It actually is free sprite 5 and sprite 2. But we're going to say, hey, we don't need sprite 5 anymore. I'm gonna delete that. So the memory allocator goes through and it says, okay, sprite free is now free, and I need to join up this sprite and say that this whole block of memory is now available. And you know, you get this thing where you can have free blocks and used blocks kind of come in and out dynamically. And it makes it a lot nicer to work with your graphics data. So all of the basic allocation stuff that you need is built into the engine. Also, man, I'm not moving fast enough. So the Game Boy Advance, I've said this a couple of times, has 96K of memory. The memory is broken up into 6 logical blocks, each of which is 16K. Each of the 16K blocks is further broken up into 2K blocks called screen blocks. The way that you interact with the graphics on screen for backgrounds is using the first 4 slots in VRAM, the first 4 character blocks. And what you do is, hopefully you're familiar with the idea of like a tile set for games and like a tile map. If not, there's tons of resources about it. Just go look up tile sets and tile maps. You load the tile sets and the tile maps into these blocks of data, background data. And that's depending on the graphical mode that you set. Again, we're using mode 2 actually. I said mode 3 earlier. We're actually using, we're using mode 0 because mode 0 is the basic mode. You have 4 regular backgrounds. So you have 4 different backgrounds that you can basically draw to the screen at any given time. You use a tile map, you stick it in one of the background data blocks, you set the registers for that background data, and then the hardware will go in and every frame it will say, let me look at this memory and see what graphical data is here, and I'm gonna draw that on the screen. So the process of drawing, I'm trying to remember here, yeah.
Are the different blocks about different storage? Are they actually rendered in different like Z layers in order?
So it's, they are blocks that are used logically by the hardware. And you, by default, so there's actually a way that you can set like which layer stuff gets drawn on. And you actually can set any background to use any character block, right? So you have 4 backgrounds. You can say, hey, backgrounds, use this specific character block for your graphical data. You can kind of like mix and match however you need, but it's just like, this is how the hardware thinks about the VRAM in mode 0, at least. So this is the other confusing thing. This only applies in mode 0. If you get into the other modes, the layout of the VRAM actually changes internally, the way the hardware thinks about it, right? So this is the joy of low-level programming, right? So backgrounds include a color palette. You can use either a 256 color palette or 16 individual 16 color palettes. You get tiles, right? We talked about tiles and tile maps. So every tile in the GBA is an 8x8 tile, and it uses one of those predefined palettes. And then you get a tile map. So the tile map says, here are all the tiles. I need to lay those out on the screen. And like this is the index of the tile I need to use for each spot on the tile. Each character block has 8 screen blocks for tile map data. So remember I said earlier, there are these 6 logical blocks in VRAM. Each of these is broken up further into screen blocks. Like you have to make sure that you align your tile map data with the screen block, the 2K blocks. The way that I organize things conceptually in my engine, you don't have to do it this way. The top 2 blocks are for tile data, and the bottom 2 blocks are for tile map data. And I just organize it like that because it's simpler. And palettes are stored in a separate place. It's pretty trivial to load those, so I'm not gonna go. Again, the color palettes, there are 512 unique paletted colors on screen. There are modes where you can get more colors than that, but you basically get 16 sprite palettes and 16 background palettes, or you can have one 256 color palette for sprites and one 256 palette color for backgrounds. You can mix and match those, but that's kind of how it's laid out. I think it ends up being like 4K of palette data. So this is like logically how the palette data is organized.
How does it address which of the 16 colors it uses with just 2 bits per, 2 bytes per color? Okay, never mind.
Yes, okay, yeah, so 2 bytes per color. We talked about the 16-bit color earlier, so you get 5 bits per each color channel.
Okay.
And then, yeah, you end up using 4 bits to index. So you have one setting where you say, hey, this is the color palette I'm going to use. And then that's 4 bits. Then you have another thing that says this is the color in that color palette. That's 4 bits, right? So you get 2 bits that way. So drawing a background, the process that you go through on the Game Boy Advance, draw background. You load the background into VRAM. Then you load the background, the palette goes into palette RAM, not VRAM. You load the background tiles into VRAM. You load the tile map into VRAM. You enable one of the available backgrounds in a background display control register. Those are the addresses, those are the bits. You configure it. You set priority when you talked about like Z depth. This sets the Z depth. You set the character base block for the tile. So you say which one of those 4 background character base blocks am I going to use for my background tiles. You set the color mode, so you tell it which type of palette you're going to use, either a 256 color palette or a 16 color palette. You set the screen base block so it knows where to look for the tile map data. You set the background size, so you say this is how big I want the background to be. And then there are 2 additional registers where you configure the offset of the background against the screen. And when you do all of that and coordinate all of that correctly, you get 1 background. Then you have to do that 3 more times to get all of your backgrounds drawn. Next, we're going to talk about sprites. So, and I was going to say, the nice thing is the engine does all of this for you. If you use the engine, you don't have to think about any of this. It does all this for you. Sprites. Game Boy Advance, again, 96K of RAM. The bottom 2 sections, bottom 2 character blocks are where you put all of your sprite data. My engine assumes that you're using 16 color sprites. So it uses the bottom 2 character blocks. And it assumes you're using mode 0 so that you can use all of those blocks for data. Drawing a sprite is very conceptually similar to drawing a background. You load the sprite palette into palette data, load the sprite tiles into VRAM, enable the sprite in this display control register. So we talked earlier about you can change the mode on the sprite on the display control register. You can also turn sprites on by flipping bit C to on. You copy sprite data into what's called an OAM buffer. So there's this section in memory called the object attribute map. Basically, it's just sprite data. It just tells you the XY position, the color mode, how big the sprite is. Horizontal and vertical flip can be done inside that data. The tile index that you're going to use to draw that tile. Priority again, so you have 4 levels of Z depth that you can work with. And then every frame, once you've copied all of this stuff into the OAM buffer, at the end of the frame, you copy all of the OAM data into actual object attribute memory for the hardware to look at, right? So the buffer is separate. We'll talk about why that's important in a bit. And then you need to load that at the end of the frame into actual memory so it can actually draw stuff on the next frame. Okay, handling input. So this, I think of all of the things we're gonna talk about is gonna like make the most sense with one little kind of nuance. So there's one register that handles input. There are 9 buttons on the Game Boy Advance, sorry, 10, counting starts at 0. There are 10 buttons on the Game Boy Advance. Each of them is given 1 bit in a hardware register. And if that button is pressed, the bit will be set to 0. This is weird.
Okay.
And I don't know why they do this. This actually has been around since the NES days. If you look at the NES hardware, high means that a button is not pressed. It's default high. I think in the NES, they did an inverter so that the coders didn't have to think about this. But yeah, so the way that it is like I'm running power through this. The bits are high. If you press a button, then the bit goes low. And so if you're looking for the A press, like this is the binary value you're looking for. And if you're looking for B and the R button pressed simultaneously, this is the binary number that you're going to be looking for. You're looking for zeros. It's actually really trivially on code to just flip that and treat it as if that's not the case. But conceptually, it's important to remember that like this is actually what the hardware is telling you. So handling input, the engine, what it will do is that it has a current keys variable and a previous keys variable. Every frame, it's going to put current keys into previous keys. It's going to load the hardware register into current keys. And then that key library that I talked about that's a layer above the hardware is going to give you 4 different options: key pressed, key released, key just pressed, and key just released. Conceptually, I'm sure you can see how having current keys and previous keys would give you the ability to do that, right? You can see if a key was just barely pressed or if it was just barely released. This is really, really useful for a lot of gameplay features. So that's why it's included. Playing audio. Don't try and play audio. It's really hard. Okay. These are the things that will definitely bite you in the butt. I got bitten by all of these. It's hard to talk to low-level hardware. I hope that you can feel by like all the steps that it takes to display a sprite or load a background that like it's really easy to mess this stuff up in so many different ways. So first off, VRAM. VRAM, I'm sure there's a reason for this. I don't understand it. VRAM is not a slice of bytes. It's a slice of UN16s. If you try and interact with VRAM as if each individual byte is addressable, it will corrupt your data. You have to address it in even addresses. If you do it wrong, you will look at your screen and say, why does this look like garbage? Go, again, does not like to share memory. I went over my solution for that. There's another solution. TinyGo offers this volatile package. And in that volatile package, it has a register 16 type. I am assured that this is great and it definitely works. I could never get it to compile. So if you can get it to compile, congratulations. I think I was missing some random DLL, or I'm on Linux, I don't need DLLs, but like some kind of code.
Shared object.
Yeah, I don't know. Something broke and I was never able to get this to work. And I've never had any issues with using Seago to get that behavior in there. But you know, if you want to be a Go purist and you don't want any header files, that's the way that you might try and break through that. The garbage collector will eat your lunch super fast. The way that the garbage collector works in TinyGo is it lets you fill up the entire heap. And once it gets a warning that says, hey, I'm going to crash, I ran out of memory, then the garbage collector kicks in and collects all of your memory. You will drop about 4 frames when that happens. It feels really bad. Actually, 4 might be generous. It might be more like 8 or 10. Like it's a huge slowdown. So what this means is you need to understand how to use TinyGo's print allocations so that you can find where you're allocating memory so that you can make sure you're never allocating garbage. Because unfortunately, if you allocate garbage, you're gonna just drop a crap ton of frames at some point. You might be able to mitigate this by forcing the garbage collector to run. You can do that. I didn't try that because I was able to simply get rid of all of the allocations to make my game run smoothly. I basically allocate everything up front and then never deallocate anything. And it's small enough that it fits inside the memory footprint. But so that's something that you're going to want to think about early. Again, we're going to come back to fixed point numbers. Fixed point numbers are way better than floating point numbers in this specific circumstance because a fixed point number is basically just an int. And what you do is when you want a fractional value, So the way I define fixed point, right, is I say, I'm gonna have a U at 16, the bottom 16 or the bottom 8 bits are gonna be my fractional bits, right? So you can interact with that as if it is a regular integer, basically. And then whenever you need to use that value, you just do a bit shift down 8 bits and you just get the top portion. And it gives you this really nice behavior of like, you can add fractional values slowly and stuff will roll over. It feels an awful lot like a floating point, but it's just an integer. And so that gets rid of a lot of those compiler complexities and issues with floating points that you run into. There are some foot guns with floating point. Division and multiplication don't necessarily work the way that you would think they do. There's a whole package on that. So if you're, again, interested in fixed point, there's lots of data out there about it. I have a big old package about that as well. Use fixed points liberally throughout your code in space of floating points, because floating point just is too slow. The Game Boy Advance is a little endian system. Endianness refers to how the bytes are ordered, which byte is most significant and least significant. So it's important to remember, you're gonna have to probably you'll steal my tools to begin with, but if you ever write tools to convert data for the Game Boy Advance, it's important to remember that it's a little endian format. So the bits have to be ordered maybe counterintuitively to what you would expect. You only have 32K of stack memory and 256K of heap memory. Remember earlier that I said audio is really hard. Part of the reason is because the audio hardware on the Game Boy Advance expects to get raw samples for you. And I don't know if you've dealt with raw audio before, but it's massive. I honestly don't really know how developers did it at all, because you got to figure out how to fit audio in 256K of RAM. And really probably what you need to do is you need to stick it inside pack read-only, the pack ROM, that's the cartridge, right? And you need to figure out a way to stream it into RAM and then stream that into the hardware registers. By the way, you can only load 4 audio samples at a time, so you have to use interrupt handlers to make sure you're always feeding new audio samples into the hardware. It's insane. Don't write an audio engine for the Game Boy Advance, but if you do, I will happily steal your code. The button input register is default high, so that's that whole thing we were talking about earlier where the bits are flipped from what you would expect. Okay, so this is an important thing that you'll see all over. There's all these people that are telling you, like, this is how you build a game for the Game Boy Advance in Go. And you'll see they have this really terrible screen tearing. And it's like, why is it doing that? So the reason is the Game Boy Advance updates at 60 hertz. And so what you need to do is make sure that you're only updating VRAM during what's called a V-blank period, right? So the Game Boy Advance draws its screen scan line by scan line, and then the CPU runs for a little bit while the screen is not being drawn. There's a period of time where there's nothing drawn to the screen and you have compute cycles. And all of those compute cycles, what they do is all the computation you just did while the screen was updating, you need to push that stuff into VRAM, right? So you compute, figure out physics, figure out collision, figure out gameplay code, right? And then now you have this period of time when nothing is happening on screen. I'm just going to sit and wait. So that's when you push all of your graphics into VRAM. If you don't do that, you're going to see screen tearing, where the top half of the screen is going to be the previous frame and the bottom half is going to be the new frame. And it looks, you would think that it wouldn't look that bad, but it looked really terrible. So if you see like weird flickering and tearing, that's what's going on. You need to have a waiting period where you're like making sure that you're only updating VRAM during that vertical blanking period. Hexadecimal and binary nibbles. The layout of binary format, how you can convert from hexadecimal into binary. Remember I said that you're going to have to go look at a bunch of C documentation. They will not coddle you. They will do hexadecimal transformations very quickly. Like, get comfortable, probably have a hexadecimal calculator somewhere where you can convert back and forth. But like, be very comfortable with that layout because that's how everything was done, right? TinyGo is great. I love TinyGo. Cannot say enough good things about TinyGo. TinyGo is not the Go compiler. If you expect the same experience, you're going to be disappointed because I have had the TinyGo compiler, for example, just hang on me for like 10 minutes. We're just like, I don't know what's going on. There's no error messages. It just won't compile. I have had it like yell at me and say, I can't compile this code. The code's valid. It's just like, I can't compile it. I don't know what's going on here, right? You're doing weird things anyways to try and like write to specific memory addresses. So Compile often as you can, be compiling your code, because at some point you're going to write code that's going to break the compiler, and then you're going to have to go through this really painful process where you comment out huge swaths of code and slowly uncomment to get the stuff that you need.
And more importantly, to your point, it will not give you errors. It will not say why it can't compile. It will just be like, sorry, good luck.
Yep, exactly. It is a wonderful tool. It has some rough edges. Be prepared for that. Okay, the last one. Whenever reasonable, consider using a lookup table. Computational resources are very, very slim. It's hard to get a lot of processing power on the Game Boy Advance. So anything you can pre-compute, you should pre-compute. I talked about, I use a sine wave for some animation in my game. I pre-compute that because I don't want to waste compute cycles trying to figure out the sine of a specific value. Okay, this is the live demo. This is the cool part that you all came to check out. So this is the Flappy Boot code base that I showed you all earlier. I have this really nice script called run. If you have the correct, you have to have the correct Game Boy Advance emulator installed, but it'll start the whole thing up for you. That looks really janky on screen, but it looks really nice for me. The animation is great, I promise.
It's the streaming.
Yeah, so you can see nice fading. That was a pain in the butt to accomplish. You have to do palette changes in order to pull that off. You can see it sits here and waits for my first input. And then I'm gonna Flappy Bird. And then you can see that if I die, then I get my best score and my current score, and I can go ahead and restart. And I get right back here and like, oh, I sucked that time, so I'm gonna quit. There we go. 6 months, that's what you get. Any questions?
Make the artwork yourself?
Yeah.
That's awesome. That's like exactly the era too.
What's next for you?
Oh man, I think I might have a slide about that. The future work, hardest to easiest. Better solution for avoiding the garbage collector would be great. You actually can do custom custom allocators in TinyGo. You can shim in your own allocator. So you could essentially do the same thing that they're doing with, what's that new thing that they just added where you can have like a giant
Arenas?
Arenas, yeah. You could do a memory arenas type solution there. Would be totally doable. Sound engine. Oh my gosh. If somebody wants to write a sound engine, that would be great. Audio is just really, really hard for all the reasons that we talked about. Debugging. Supposedly, most emulators offer a GDB server where you can like inject debug information and then debug as the emulator's running. I've never been able to get it to work. I tried for probably 2 or 3 hours. That's not a long time, but that would be incredibly helpful. If you think that printf debugging is like primitive, you don't even get printf debugging on the Game Boy Advance. You've got to be able to draw like pixels on the screen and be like, oh, there's a red pixel there. That means this is where I failed. Like that's the debugging that you end up doing. This leads into a text system. Text system would actually be pretty easy. You just have to make the font and then load the sprites in. And that's, I think, fairly trivial to do, especially if you're doing fixed width. Hardware interrupts. Hardware interrupts are totally supported. I didn't get around to implementing them in my engine specifically. If you don't know what a hardware interrupt is, you can have specific points where the hardware says, for example, we talked about those scan lines, right? You could say, hey, hardware, when you're done drawing the screen, interrupt and run this little piece of code right here. That's how you're supposed to do it. The way that I did it is like the janky hack where you like peek at which scan line it's drawing and like just run a tight loop on that until the opportunity presents itself. But like hardware interrupts are really great. Better error handling. I don't really have any error handling that bubbles up well and presents well. Better TinyGo docs. This is something that I totally need to just go and do. I learned a ton of stuff here that just doesn't exist anywhere else on the internet. I just need to go and write it down inside TinyGo. If somebody else plays around with this and decides that they want to get some kudos and drop some documentation in TinyGo, be my guest. That would be amazing. And more games. I just want to build more games. So yeah, in the back.
I'm curious on like hardware speed. Is the emulator like good at slowing it down to be accurate?
Yeah, I mean, either that or my game would never run on actual hardware. I never actually tried it on actual hardware, but I definitely ran into situations like the floating point example earlier, where I was noticing dropped frames. Seems like most emulators are pretty accurate in emulating slowdown. And that makes sense because there are actually games that kind of relied on that. Like if you ever played shoot 'em up games or anything like that, where when it gets really intense on screen, there's lots of explosions and stuff. The game like slows down, and that's kind of like an intentional game design choice. So I think that the emulator developers focus on like, that's part of the experience, so we need to support that. So that seems to be fairly well represented, at least in the emulator that I use, which is, oh crap, let me find it for you.
MGBA.
It is, I can't remember if
It was
it's
MGBA, that's what I saw on screen.
see. Yeah, MGBA QT. So the important thing is you want the QT because that gives you all of the extra like debug stuff that you're gonna want to look at. So, and then you,
Yeah, I mean, the question I have seems to have been answered by some of your previous points, and I was just gonna ask about visibility. Like, I think I already knew the answer. There wasn't probably a lot of great visibility. Like, is there a way to like print at the top of the screen, like, oh, this is how much memory you have right now. This is how many frames you have right now. So at least while you're playing, like you can kind of get a pulse reading for how you're doing for that stuff.
yeah. So, okay, so this is why you want MGBA QT, and this is a great question. So, not all emulators provide this. MGBA QT does. So you do have access to these tools. So for example, I can go look at the IO registers. So this tells me this is what the configuration of the display control register is currently set to. It looks like you can come in here and toggle these. Sometimes it works, sometimes it doesn't. Okay. So you can go in and toggle different hardware registers and play around that way. There is also, and I have used this before, you can search memory. So if you want to write text to a specific memory address, you can go look up that memory address and see what text got written there. That's one way. You can look at, is it view memory? No, yeah, view memory. So this is just a layout of all of the memory in the Game Boy Advance. So like if you're trying to figure out, hey, why are my palettes weird? You can go and actually look at the raw data in the palettes. Like these are really the most powerful tools that you're going to want to use. But yeah, because there's no text system or anything, like I have, in fact, I probably can show you guys. There is a tile set. And where is it? Oh yeah, debug tile set PNG. Oh, and these are so small. I don't know if you can see
You
these.
gotta open up the raw if you want to zoom into the image.
Oh, okay.
Like, where's raw?
I've zoomed in too far and now I can't find anything. Well, anyways, there are some images that I specifically add into the emulator as sprites so that I can, like, when I was doing collision detection, right, I had like circles that I could place and be like, this is the bounding box of the collision detection. So you can do stuff like that. The tough thing is if you don't have the ability to draw sprites yet, it's really hard to debug because you can't draw sprites to help you debug, right? Like there's definitely a threshold that you have to get past before you can get like any debug information. So that's kind of a tough threshold to push past. And one of the reasons why I would highly encourage you to steal from me, because I'm past that point, so you don't have to like try as much as I did.
Has to pull your hair out point.
Yeah, exactly.
Are there any other high-level languages that you can do this with?
So yes, actually. So Rust has, if you wanna build a game for the Game Boy Advance and you want it to be this small teeny project and you want to do stuff in Go, then totally do this. But if you want to like build a game in Game Boy for the Game Boy Advance, do it in Rust. Don't do it in Go. Rust has a way better ecosystem. It has way better tooling. I wish that my stuff was as good as Rust stuff. There's a package called AGB, and it's awesome. Go use that. Also, if you're like, hey, Go is hard and confusing, there are systems out there that let you program Game Boy Advance games in Lua. They will be way more resource constrained than even this. So be very conscious of that, but you can totally do it. There are people who have built like scripting languages, or like scripting support. So you can have a Lua game written in Game Boy Advance. It's, I think, backed by C++. But yeah, those are like the two big ones. If I was gonna write like a commercial GBA game, which these actually exist, there's a game in development that's gonna be released on Steam that's being written for the Game Boy Advance. I would write it in Rust. That's personally where I would go.
Oh, was it the dog one?
Yeah. I forget what it's called, but yeah, it's kind of cool. Cool. All right. Well, I think we'll wrap up, and then if there are any lingering questions, I'll be here, so you can hang out.